recap, the birth of a star occurs from a nebula or a stellar nebula, either a nebula or a stellar nebula. So a stellar nebula is a bunch of hot gas. A nebula is a bunch of hot gas. What's the difference? The stellar nebula is formed at the death of a star, but a nebula itself is called the first nebula. When we just say nebula, we mean the first nebula, which formed after the Big Bang, just by the accumulation of the hydrogen gases that were first created. So that's the first nebula, and then every other nebula is basically stellar nebula. Okay, so and then there is also planetary nebula. Last class, I like আমি খুব ফাস্ট বলতে গিয়ে একটু ভুল বলে ফেলছিলাম. Planetary nebula has actually nothing to do with planets, although the name suggests. Planetary nebula we will study here. Average star to red giant. When an average star becomes a red giant, it becomes a planetary nebula. So a planetary nebula is actually another stage in the life cycle of a star. Okay, so that has nothing to do with actually this type of nebula. Anyway, so from a nebula we have the star. How do we get a star from a nebula? If you remember, we studied last class, this is a nebula, right? The Orion Nebula. I told you we could see it where, like right below the Orion belt, right? Okay, so what is a nebula? Over very long periods of time, the force of gravity begins to bring together clouds of hydrogen gas. You remember? The gravity brings together clouds of hydrogen gas, and then as these clouds form, they get smaller and smaller because the force of gravity is acting on them. And as they get smaller and smaller, so the distance decreases. So the force of gravity becomes stronger and accelerates the process. So this collapsing gas or collapsing cloud of gas is called a nebula, and it's the first stage in the evolution of a star. Okay, so what happens next is, at the core of the star, when the core of the star gets really hot, because as the nebula gets smaller and smaller, the there is huge attraction force, right? So that huge attraction force causes the particles, the nuclei, to accelerate to very high velocities, the hydrogen nuclei. So the hydrogen nuclei accelerate at very high velocities, so they get huge amounts of kinetic energy, which means there is huge amount of temperature and pressure. As there is huge amount of temperature and pressure, sorry, you have as anyway. So as there is huge amount of temperature and pressure, so that temperature and pressure causes the hydrogen nuclei to overcome their electrostatic repulsion. Fancy word of saying positive repels, right? So hydrogen nuclei, basically they repel each other, but that repulsion that repulsion force is overcome. Why is it overcome? Because of the huge amount of kinetic energy, high temperature and high pressure. So that overcomes the repulsion, and therefore the hydrogen nuclei basically bump into one another, and basically what happens is they form they join together to form a larger nucleus, and this is called a nuclear fusion reaction. This is called a nuclear fusion reaction, and we will study more about nuclear fusion reaction in later in this chapter, and also we will study nuclear fusion reaction in radioactivity section. Okay, so this is nuclear fusion reaction. So nuclear fusion reaction, I didn't say much about it last class. So nuclear fusion reaction is basically, we know nuclear bombs, right? We know about nuclear bombs. We know the history, Hiroshima, Nagasaki, the sad history. So nuclear fission reaction produces huge amount of energy. We know that. Now think of like tens and hundreds of nuclear fission reactions, or more, or even more. I don't know the exact value, but tens of 100 times more energy than a nuclear fission reaction from is produced in a nuclear fusion reaction. So that is nuclear fission, FISSION. We will study that in radioactivity. And this is nuclear fusion, FUSION, fusion. So nuclear fusion reaction is basically, the difference is basically, in nuclear fission a large nucleus breaks down into two small nuclei. However, in nuclear fusion reaction here, two small nucleus join together to form a large heavy nucleus. So that large heavy nucleus in this case will be helium. So basically what happens is two hydrogen nuclei, they join together to produce helium, and that is why at the core of stars continuously helium is being produced, at least in the core of our sun and many other stars like the sun. We will talk about those in the future slides. But so this nuclear fusion reaction, since it's a huge reaction, it releases a lot of energy. As it releases a huge amount of energy, this energy goes away from the center towards the surface. Okay, goes this energy tries to escape from the center to the surface. So this is the this propagation of the energy produces an outward force, and that outward force is called radiation pressure, that we learned in last class, radiation pressure. So basically the nuclear fusion reaction that occurs at the core of the star, it produces a huge amount of energy, so that energy wants to travel to the surface, so it produces a outward force that is called radiation pressure. As the energy makes its way, okay, so what do you have? What's the result of all of this? The result of all of this is a hot ball of gas, right? A ball of gas that is very small, because it got smaller and smaller due to gravity. But again, remember, when we say small, we don't mean small in our scale, we mean small in astrophysics scale. In astrophysics scale, the sun is a like medium sized star, okay, because it's not that big. Okay, there are huge stars. So this is a small star, this is a small stage of the star, protostar. Even this will be like bigger than any planet. Okay, so that's the protostar phase, but it's a very hot ball of gas. This hot ball of gas, and there are two forces acting at work here. Okay, there are two forces at work. What are the two forces? Number one is the gravitational force that is pulling all the gases together towards the center. So the gravitational force is trying to make the ball smaller and smaller. What's the second force? The second force is the outward force. What do we call it? We call it the radiation pressure. So there are two forces. It's like a tug of war, right? Inside, imagine like someone is pulling into a circle. Someone is pulling into a circle using a gravitational force, and you are pulling out that same object using a radiation pressure force. So it's a tug of war between these two forces, right? Now in protostar phase, the force of gravity is stronger. So what's gonna happen? The star is gonna get smaller and smaller. However, what happens is, as the star gets smaller and smaller and smaller, what also occurs is that as the star gets smaller and smaller, what also occurs is that the protostar, at the center of the protostar, the nuclear fusion reactions become more and more energetic. Okay, because the smaller the star gets, the higher the temperature and pressure gets, and more fusion reactions start to occur. And as more fusion reactions start to occur, let's go to the next slide. As more fusion reactions continue to occur, so as the nuclear reactions continue, the high temperature create forces that try to push the particles apart, that is make the gases expand. So as the nuclear reactions continue, what does this cause? The more the nuclear reactions, the more the outward radiation pressure force, right? So as the radiation pressure force increases, what will happen? The star will try to blow up, like it will try to expand, because remember the tug of war, the radiation pressure force is outside. It's trying to pull the molecules out from the center, and the gravitational force is trying to pull the molecules inside into the center. So the radiation pressure force basically makes the star slightly expand, makes the gases expand. Now, so it's like this: the gravity tries to pull it inside, but the more the gravity pulls it inside, more nuclear fusion reaction occurs. So the outward pressure force, the radiation pressure force increases. So the star expands again, and then as it expands again, gravity again pulls it down. So at at one point, this becomes balanced. That is, the gravitational force and this outward push, that we will from now call radiation pressure, is balanced. Okay? The star is said to be in its main stable period. It is referred to as a main sequence star. So this is a main sequence star. It's the most stable state of a star because, as you know, as you can tell, that the tug of war is now balanced, so it's gonna stay like this, right? There is no reason for something else to happen. All right, like the gravitational force and the radiation pressure force are exactly balanced. So obviously, in comparison, just to make a comparison, you see, for a one solar mass star, I'll get to this in a minute. The protostar phase lasts about 1 million years. After that, it becomes a main sequence star. So, like the small star, the small hot ball of gas, it stays a small hot ball of gas for about 1 million years, and then it blows up and expands into this, a sun-like star. Okay, you can see this diagram. Like the small guy now becomes this sun-like star. So this occurs over time and it takes about 1 million years. However, this phase, as I said, this is the main sequence star. It's the main stable period of the star. It's the main stable state of the star. So this state stays much longer. This period can last for many millions or even billions of years. At the moment, our sun is in this stable period. Okay. Acha. What is meant by one solar mass? Okay, I should define it right here. Um, one solar mass is the mass of our sun. Actually, it's a very simple definition. One solar mass is the mass of our sun. But what does this mean? What is two solar mass? If a star is two times smaller than the sorry, if a star is two times larger, two times more massive, larger, smaller, বলা কোনোটাই উচিত না. If a star is two times more massive than the sun, then it is a two solar mass star. If a star is half the mass of the sun, then it will be a 0.5 solar mass. Okay, so 0.5 solar mass star is like half the mass of the sun. Half the mass of the sun. Two solar mass star is twice the mass of the sun. Get it? So that's how it works. So solar mass is a large unit of mass. Just like light year is for distance, similarly solar mass is for mass measurement in the large scale of astrophysics. Okay. Now, any questions so far up to main sequence star? Walaikum assalam to everyone. ওকে, সব স্টারের শেপ বলের মতো কেন? ইন্টারেস্টিং কোয়েশ্চেন। Why is everything spherical? Not just stars, actually, planets, moons, everything in the astronomical scale is spherical. Why? This is a very interesting question. Although this is beyond this topic, I'll say this anyway. It's like sphere is actually the most stable shape in terms of pressure and all the other equilibriums. Okay, like if Earth was a box, or if the Sun was a box, if it was a cube, then it will collapse under it due to its own gravity. The corners will collapse due to its own gravitational pull, until the Earth again became a sphere. So sphere is actually the most stable um, shape in the entire in our entire universe. Okay, you can knock me later, or send me a message later. I'll send you a video explaining this. There's a really nice video explaining this. Anyway, um, sir, hydrogen supply শেষ হয়ে গেলে কি সানের? Yes, hydrogen supply. When the hydrogen supply is over, what happens we will study in the next slides. Radiation pressure. Radiation pressure is nothing but the um. Have you ever seen a grenade explode? There's a force, right? There's a force outward. That outward force is radiation pressure. Like, it's not called radiation pressure in case of a grenade, but in case of a nuclear fusion reaction, it's called radiation pressure, because something is a huge reaction is occurring in the center. So obviously a large force is gonna go out in all directions because the energy is trying to escape to the surface. So that's radiation pressure. That's the outward force. That's the radiation pressure. Fake. It will be better if you don't use fake names. Then I will not understand whose question is which. So those who are using it, rather change it. Anyway, um, okay. So back to our topic. What is a solar mass? I will explain this one again. Solar mass is a unit of mass. Okay, so let me specify that here as well. Solar mass is a unit of mass. Okay, kilogram is a unit of mass, gram is a unit of mass, pound is a unit of mass, or maybe for that mass, and also similarly solar mass is a unit of mass. Okay, so it's a unit of mass, that's it. So how much mass is one solar mass? Okay, well, the problem with the sun is that it's big. Ah, damn it. Network problem. Uh, okay, now to repeat, the solar mass. Solar mass is a unit of mass. One solar mass is the mass of our sun. Now the problem is the mass of our sun is huge. It's 1.9891 into 10 to the power this just means into 10 to the power 30. 10 to the power 30 kg. So yeah, it's huge. 1.98291, I don't even need that. I'll just approximate it to this. About 2 into 10 to the power 30 kg. That is a huge mass. Okay. Now, if you want to say, if so that is why we go to the unit of solar mass for to make calculations easier. Okay, so one solar mass is the mass of our sun. So what is two solar mass? Two solar mass is twice the mass of our sun. That is, two solar mass will be 2 into this many kg. What is 1 kilometer? 1000 meter. What is one solar mass? 2 into 10 to the power 30 kg. What is two solar mass? 2 into 2 into 10 to the power 30 kg. What is 3 solar mass? 3 into 2 into 10 to the power 30 kg. What is 0.5 solar mass? 0.5 into 2 into 10 to the power 30 kg. Get it? It's just 0.5 times the mass of our sun. 2 solar mass means 2 times the mass of our sun. 3 solar mass means 3 times the mass of our sun. That's it. It's a unit of mass. I hope that clears the question. Okay. Um, Alright. I hope main sequence, up to main sequence, you do not have any questions. So I'm moving on to the next stage. But okay, before we go to the next stage, I'll read the reading material for you of main sequence star. So stable main sequence star. When the radiation pressure is strong enough to balance the gravitational force. Oh, sorry, you're not seeing it. What is happening? Hello. Yeah. Okay. Okay, this is super confusing. Okay, yeah. Um, where are we? Yeah. So when the radiation and pressure is strong enough to balance the gravitational forces within the nebula, it will stop collapsing and a stable star is formed. Okay, a stable star is formed when the balanced gravitational force and radiation pressure balance each other. Okay, so our nearest star, this is just an example, we'll all skip through it now. Stars which formed from larger nebulae will obviously form into more massive or giant stars. The gravitational forces trying to compress these stars will be much larger than those of our sun, and they will require much larger radiation pressure to keep them stable. These stars will therefore be much more powerful and brighter than our sun. Do you guys understand this paragraph? This is very important. Let me clarify this again, okay? Stars can form from a small nebula or a large nebula, from a small protostar or a large protostar. That is, the protostar phase, as you can see, is not in your reading material. There's nebula and then main sequence stable star, because the protostar phase is not in your syllabus. Also, the protostar phase is not much important compared to these, in my opinion. But so basically, from the nebula we get to the main sequence star. Even in between, there is a protostar phase. That's when the planets form. Okay, anyway, we discussed that last class. If you have confusion, you can rewatch that video. Okay, so now stars can form from a large nebula or a small nebula. If a star forms from a large nebula, that means the star is being formed by a larger mass of hydrogen gases. Yes or no? Yes, it's a larger mass of hydrogen gases, right? So it's a larger mass of hydrogen gases. Larger mass means larger gravity. Remember that? Gmm by r square. Force of gravity. Gmm by r square. You remember the formula, I hope. That's from our first class. So Gmm by r square. So the larger the mass, the more the gravity. Simply, the larger the mass, the more the gravity. If you can recall that much, that will be alright for now. Larger the mass, the larger the gravity. Alright, so the larger the nebula, there are more hydrogen. The more hydrogen you have, the more mass you have. So if a star is being formed from a larger nebula, the star will be a more massive star. That is, it will have more mass. So we call them giant stars. Okay, more massive or giant stars. You with me so far? Giant stars. Large nebula, giant stars. Okay. Now, like I said, more massive. So the gravitational force will be much larger. Gravitational force, and what does the gravitational force try to do? Does it try to compress or expand? You need to remember this. The gravitational force tries to compress, and the outward push, that is the radiation force, tries to expand the star. These are the two forces at play. Gravitational force tries to compress, and outward radiation pressure tries to expand the star. So, since it will be more massive, so the gravitational force trying to compress these stars will be much larger than those of our sun, because this star that we are talking about, the star we are talking about here, is formed from a larger nebula, so it has a larger mass, so it is a more massive or giant star, so it has more gravitational force. So the gravitational force trying to compress these stars will be much larger than those of our sun. Clear? So now, if you have more fat guys on the left of a tug of war, then you will need more fat guys, more strong guys on the right as well to balance, right? Okay, so if the gravitational force is larger, to balance the gravitational force now, who needs to be larger? Who needs to be larger? The radiation pressure. The radiation pressure now needs to be larger. So for these massive stars, the gravitational force is larger, so the radiation pressure must also be large. The radiation pressure must be huge. Therefore, now the question, what causes radiation pressure? Do you remember this? What causes radiation pressure? Nuclear fusion reaction. So, if you need larger radiation pressure, you are gonna need more nuclear fusion reactions, which means you're gonna have, if you have more. Now how can you have more nuclear fusion reactions? If you have more gravitational force producing a higher and higher temperature and pressure. So if you have, so you we already talked about this, you have large mass, this not you, the star, okay, chill. Now the star has large mass, and so it has huge gravitational force pulling it in. Therefore, it also has huge amount of nuclear reactions going in, because going on at its core. This is because since the gravitational force is higher, so the temperature and pressure at the core of this star is higher than the temperature and pressure at the core of a smaller star, for example our sun. So the temperature at the core of our sun is lower than the temperature at the core of these massive stars. So since these massive stars have a higher temperature and pressure at their cores, therefore they can have more energetic and more frequent nuclear fusion reactions. Therefore, these nuclear fusion reactions will produce more and more energy. As these nuclear fusion reactions produce more and more energy, therefore, these stars will be more powerful and brighter than the sun, because they have a higher gravitational force, so they must have a higher radiation pressure, and to produce that radiation pressure due to the gravitational force, they are carrying out more and more nuclear fusion reactions, and therefore they are releasing more and more energy. So these stars are more powerful and brighter than the sun. What you need to remember, very important here, is if a star is more massive, then it will be more powerful and brighter. The more massive and more powerful. More massive means more powerful and brighter. Okay? You can write this down. Just no, you can just jot this down, okay, as a short note. More massive, more powerful and brighter. Okay? And you understand the reason why. More massive, giant stars gonna be. Okay, let's see if any question here. Okay, let me answer some questions now before I go to the red giant phase. Um, so size of a star depends on the size of the nebula. Yes. So size of nebula also technically depends on size of nebula. Yes, Rafin, it's a nice paradox. So yeah, size of nebula actually depends on the size of nebula because, well, the first nebula was huge, so it produced some huge stars, and then those huge stars, when they died, they also produced huge nebula, which again further produced huge stars, and so on. About sending you the PDFs, I have uploaded two large PDF files in the group before last class. Okay, so like two classes earlier, and those two PDF contains all the contents of astrophysics. Okay, all the contents of astrophysics, at least, like, so those two PDFs cover. I'm just going to tell you this. Like this PDF that we're reading right now, you have this full PDF. It's a 37-page PDF, and I'm only on page 17. Okay, so you just read the PDF with me. And also in the slide, if you can see in the slide, we are only on what, slide 9 out of slide 14. Okay, so yeah, I've already uploaded the whole slide. Just here. So yeah, so I won't be uploading PDF after this class either, because I've already uploaded this lecture materials on the group, on your group. Okay, any more questions? Can you guys not make fun of each other here so that I can actually focus on the questions? Can we make a star blow up to create another? We'll get to that in a minute. Okay. What does radiation pressure do? What does radiation pressure do? It expands the star. I've been telling you this. Radiation pressure, what does it do? It's just a force that is expanding the gases because the energy wants to escape. The energy does not want to remain at the core where it is produced because it wants to spread out. Energy always wants to spread out. Okay? That's radiation pressure. Tamasha asked, if the first generation star is large, then the second generation star will also be that much larger? Not necessarily. There are a lot of factors into play, most of which are random to our best of knowledge, at least to my best of knowledge so far. So yeah, most of them are random. How big a star will be depends on the nebula, depends on the gravitational forces, depends on how many stars are gonna form, depends on a lot of factors. Depends. That's the answer of this question. Radiation pressure, yes, similar. Pressure from bomb and radiation pressure, very similar, yes. Okay. Yeah, there was some lag. Sorry about that. I think it's fine now. The stream is all right now. Okay. Now, the life of a star, protostar to sunlight star. We have covered this far. Oh, sorry. Yeah. We've covered up to here. Protostar to sunlight star. But now to red giant. Now this is the point where we start talking about future. Okay, so of course these are scientific predictions with the best of scientific knowledge that we have so far. Okay, now you may ask, how do we make these predictions? Well, because there are, like I said in the first class, billions of stars, billions of galaxies. So there are lots and lots of stars that are just like our sun. So we have seen most of those stars undergo these transitions. They this has been the future of all stars that are like the sun, like in terms of mass, nuclear reactions, and everything. So we can make the same predictions for these stars, our sun as well. So basically, how we're going to study this is we're going to study two types of predictions, or like two types of life cycle. What happens to a star? Okay, so think of it like a life cycle that we know rather than a prediction, because um, if you are to tell that a new human baby is born, and you're gonna say that this baby, if everything goes right, he is gonna grow 10 years older, then he's gonna go into teenage where he's gonna be a bad boy, and then he's gonna correct himself again in his 20s where he will question life choices, think about philosophy and all that and whatnot, and then eventually he'll become an adult, and then he will become old, and then coronavirus dies anyway. Okay, jokes apart, the idea is, you can now are you did you just predict the life cycle of that child? No, not really. I just said the typical life cycle of a human being. Similarly, what we are studying here is the typical life cycle of a star. So there are two typical life cycles. One is for the average star, or also called low mass star. Low mass. So these are the small guys. Alright, like the sun, chilling guys. Low mass stars. Not that big deal. And then the large mass star, like huge massive star. Massive stars and average low mass little guys. Okay? So they follow one life cycle, and the massive stars follow a totally different life cycle. Okay, and we're gonna get there. Yes, I know you're looking at this, so yeah, we're gonna get there. Okay, we are gonna get there, I mean we're gonna study it to that point. But sadly, our son is which guy? This guy. So he's gonna end up to this life cycle. He's never gonna be, our sun is never gonna be as cool to as or rather as hot enough to become a black hole or a neutron star. No, it's just gonna become a white dwarf. It's gonna turn out as a dwarf. Okay, anyway, so the life cycle of a star, is our connection all right? Yes, the connection is all right. Now, the life cycle of a star beyond the main sequence. Okay, so what was happening there in the main sequence period? In the main sequence period, the hydrogen was fusing into another more hydrogen and then forming helium, right? So where is that helium that is forming? Hydrogen is bumping into hydrogen and causing nuclear fusion reactions and producing helium. Where is that helium going? That helium is staying, obviously, at the core of the star, right? At the center of the sphere. At the center of the sphere, that helium is getting accumulated, or rather just getting together, alright? So yeah, it's getting accumulated. That's a proper word to say. So now, obviously, as more hydrogen is burnt, by burnt we mean nuclear fusion, okay? As more hydrogen is burnt, the core gets more and more filled with helium, right? It's like, if you burn a lot of coal, you will produce a lot of ash, right? Just like that, at the core of the star, as the star burns a lot of hydrogen, or rather causes nuclear fusion between a lot of hydrogen, the more hydrogens fuse together, the more helium nuclei are produced. Okay? Now here's the fun part. So, rate of fusion decreases as density of hydrogen decreases. What? What is happening? Rate of fusion? Rate of fusion means simply how many fusion reactions are occurring per second. So, like rate of collisions, rate of fusion. So, rate of fusion. Rate of fusion decreases. Why does it decrease? As density of hydrogen decreases. Understand this. You have a ball filled with, actually I'm gonna draw this for you guys to have a better understanding. Why- sorry, yeah. So let's see if you can have a better understanding. Okay, I want you guys to really, this is pretty cool stuff. So let's say this is the sun. I'm gonna make it, sorry about that. Yeah, this is the sun, and now it's getting the core. So imagine initially all of it is hydrogen. The yellow things are hydrogen. And now I'm gonna draw this in black. The black part is helium. Okay? So initially you have this much hydrogen in this much space. Right? Like you have the whole space filled with hydrogen. But as more and more nuclear fusion reactions occur, the core keeps getting bigger and bigger, right? So once the core becomes like this, it still stays at the center. Okay, you get the point. The As the core becomes bigger and bigger, yeah, okay. As the core becomes bigger and bigger, now what do we have? We have just this much amount of just the yellow part, amount of hydrogen in the same amount of space, because the total volume of the star did not change, but the amount of hydrogen has decreased. So density is mass by volume, right? So there is now basically less hydrogen per unit volume. So as the density of hydrogen decreases, rate of fusion decreases. Okay, because there are less hydrogen per unit volume, so there are less frequent collisions between hydrogen nuclei, and as there is less frequent collisions, so there are just less energy produced, less fusion reactions occurring. Okay. All right. Then I think we have some buffering. Sorry about that. Okay, I think it's all right again. What are you guys saying? Okay, I'm gonna read your questions for a second. Uh, sir, temperature matter or not? Temperature depends on mass ultimately. So yeah, it all depends on the mass. Precipitate? No, it's nothing like a precipitate. I don't know what you're asking. Sun will become a red giant. Yes. If the sun, I'll get to it. Yes, right, Rafin, I'm saying exactly that. Small guy, less hot, average. is 1 in trillions to have a habitable sprawled star in the galaxy. Can we burn us on fire? Okay, so yeah, it's just I'm telling you, this is not burning in the sense of burning. This I'm just saying nuclear fusion reactions. Okay. Anyway, moving on. So the connection will be all right. All right. It's lagging a little, but it's gonna be all right. Thank you for your patience. Yeah. Okay. So like I was saying, the as the density of hydrogen decreases, the rate of fusion decreases. Okay. So as rate of fusion decreases, gravitational attraction becomes more dominant than outward kinetic energy and compresses the star. Understand this? Like you previously there was a lot of hydrogen fusion reactions, so there was a lot of radiation pressure. But now there are less fusion reactions because the rate of fusion has decreased, because the density of hydrogen has decreased. Sorry about that. Okay, so rate of fusion decreases as hydrogen density of the hydrogen decreases, and also as the gravitational attraction becomes more dominant than the outward kinetic energy and compresses the star. Okay, because you need to understand that as the as the nuclear fusion reaction rate of fusion reaction is decreasing, as the rate of fusion reaction is decreasing, but the gravitational force has not decreased, right? It's the same gases. It's more helium, but the essentially the same mass. So the mass of the star is the same. So the gravitational attraction force that is pulling it inward is the same. But as the rate of fusion has decreased, so the outside radiation pressure that was pushing the star outward, the outward radiation pressure, outward Ke, or rather I'll say outward radiation pressure. So as the gravitational attraction becomes greater than the outward radiation pressure, because the outward radiation pressure is now smaller, so the star is compressed. So the sun, after it has burnt out most of its hydrogen, you already asked me this question, that what will happen when the sun has almost burnt out all of its hydrogen. Well, not all of it, but you see, like this, when it has burnt out most of its hydrogen, then the density of hydrogen will decrease and the rate of fusion will decrease. So the outward radiation pressure force will decrease, and the gravitational attraction will become more dominant, and so the star will start to compress. However, so the star starts to compress. However, as the star shrinks in size, there is a large increase in temperature, right? Because yeah, as now that the star is compressed, there is more temperature. There is a large increase in temperature because it's now shrinking. So now now the density will again increase. Now there will again be more collisions, because like right now it looks like the density of hydrogen is smaller, is very small, right? But if this star itself becomes smaller, now we have like this will also get smaller in the same proportion. So now we have the, the same amount of hydrogen but at a smaller space. Now that we have the same amount of hydrogen at a smaller space, therefore the star will actually there will actually be an increase in temperature, because there will be more collisions, more hydrogen, same amount of hydrogen in a smaller space, more collisions. More collisions means higher temperature. more collisions, more kinetic energy. So more kinetic energy means higher temperature. Now, um, this is kind of, oh, skip this. This is okay. After this point, let's go back to our reading material. Now, let's read what we have already studied. Although the balance between the inward force of gravity and the outward force of radiation pressure in a main sequence star can allow the star to shine with a fairly constant output for several billion years, the hydrogen fuel, is not actually fuel, but we're saying fuel, required for nuclear fusion will eventually run out. When this happens, the core of the star begins to collapse under the relentless pull of gravity. This increases the temperature and pressure at the core of the star. So this we have studied up to this. Alright? Now, now that the temperature and pressure has increased at the core of the star, what will happen? Now, allowing it to start fusing the helium in its core to produce more energy and therefore radiation pressure. So what happens now? What happens now is, you see, in main sequence star, which fusion reaction was occurring? Which fusion reaction was occurring in main sequence star? Which nuclear fusion reaction? Hydrogen nuclear fusion reaction, right? Nuclear fusion reaction between hydrogen atoms, hydrogen nuclei. So hydrogen nuclei were fusing into one another and producing helium. But those helium nuclei that were being produced, they were not fusing into one another. Why? Because hydrogen fusion requires high temperature and high pressure. Fine. However, helium fusion, the fusion of helium, requires even higher temperature and pressure. The fusion of helium requires even higher temperature and pressure. So now that the star has began to collapse due to its gravity overcoming its uh, radiation pressure force, as the core of the star begins to collapse under the relentless pull of gravity, and the temperature and pressure has increased at the core of the star. So now the temperature and pressure is high enough for helium fusion to occur. Okay, now the temperature and pressure is finally high enough for helium fusion to occur. And so remember how hydrogen fusion, how I told you that hydrogen fusion produces huge amount of kinetic, a huge amount of energy in general, like way more energy than nuclear fission reactions, way more energy than the atomic bomb. Well, guess what? Helium fusion reaction releases even way more energy than hydrogen fusion reaction. The fusion of helium produces even more energy. Okay? And the more energy that is produced by nuclear fusion reaction, that will mean more outward radiation pressure, right? The more energy you will have, there will be the greater outward radiation pressure. Got it? Okay, so what will happen? This radiation pressure pushes the outer layers of the star, causing it to swell up dramatically. So the now suddenly helium fusion occurs, and now the radiation pressure is so high, it's actually higher than gravity. So up until now, gravity became higher than radiation pressure because fusion reaction was slowing down, because hydrogen was running out, right? And so the star started to collapse because gravity was becoming dominant. But now all of a sudden, radiation pressure is dominant because of the fusion of helium. Radiation pressure is dominant, and now the star starts to swell up. That is like it starts to like blow up like a balloon. You know, like how a balloon blows up. The star now starts to swell up dramatically. It has been calculated that when the sun runs out of hydrogen fuel, its outer layers will grow to a point beyond Mercury, Venus, and the Earth will be swallowed up. Mercury, Venus, and Earth. Do you guys remember the solar system diagram? Mercury, Venus, Earth, Mars, Jupiter, and all that, right? So Mercury, Venus, Earth, all the way up to that will be the sun itself. It will be so huge. It's gonna swell up so much. Okay, when the sun runs out of hydrogen, that's what's gonna happen. But lucky for us, when is the sun going to run out of hydrogen? About about 1 million years later, at least a million years. Okay, I think I told you the value. Like, yeah, many millions or billions of years. Okay. Oh, sorry, my mistake. 5 billion years. Our sun is expected to undergo this change in 5 billion years. I just told you million, not million. 5 billion years. So we have time. 5 billion years later, this will happen. So we don't need to worry about that now. Anyway, now, as the outer layers of the star are now much farther from its core, now what happens when the star has swallowed up, like has swelled up this dramatically into this huge star? It's now a huge star, right? It's now a very large star. But the problem with a large star is the density is lower, right? Because it has the same amount of matter. The matter is the same, like it's the same amount of hydrogen and helium, but now it's in a much larger volume. So the density is now lower. As the density is lower, so there are less collision, less kinetic energy, therefore less temperature. So even though the sun, when it swells up, or any star when it swells up and becomes very large, it actually cools down. That is, the temperature becomes lower. And if you remember this, now this is getting really difficult for you, maybe remembering so many stuff, but if you can recall this chart that we studied in last class, this chart, yellow is about 6000 to 5000 Kelvin surface temperature. So now that the star has swollen up, so it will cool down and it will become red, a low temperature, a very low temperature star, a very cold star. We are saying cold, but what is cold? 2000 to 4000 Kelvin temperature. 2000 to 4000. You can just say it's almost like 2000 Kelvin is what? About 1700, a little more than 1700 degrees Celsius. Right? So huge surface temperature, huge. But this is a very cold star. In comparison to other stars, this is very cold. Okay? So I'm gonna skip this. Uh, so there is a large increase in temperature and pressure. So helium fusion is now triggered at the core and hydrogen fusion continues on the surface. Okay. Now the helium fusion reaction releases a lot of energy which is sent throughout the star as a shock wave, and hence the star expands to many times of its original size. As it expands, it becomes a little cooler and the star is changing into a red giant. Is this clear? So it has now changed into a red giant. And our sun is expected to undergo this change about 5 billion years later, when it will expand beyond the orbit of Venus and swallow up the Earth. Okay? Yeah. Alright. So, what will happen after the red giant? We will study that in the next class. What happens after red giant, okay? It will finally become a white dwarf. Anyway, so for today's class, if you have any questions now, I'll answer your questions and then I'll end the class. Any questions? FBI open up. What will happen when it uses up all the hydrogen? Well, it will never really use up all the hydrogen. There will still be some hydrogen left in the surface. But remember the black circle I drew? The black circle is gonna get bigger and bigger. Okay, that's it. So basically helium, it's gonna get more and more filled with helium. But once it has become a lot of helium and less hydrogen, it will become a red giant like I just described. And after it becomes a red giant, it will start also consuming or rather burning up, that is by nuclear fusion. It will also start fusing the helium nuclei, so the helium nuclear reaction will continue, so it will continue. I'm sorry if there was some lag in between. Okay, so kindly please rewatch those parts, and also if you have any questions regarding those parts, just tell me what you missed, I'll repeat that. Okay, pull of gravity কোথায় থেকে আসে? Pull of gravity আসে from mass. Every mass attracts other masses. So every hydrogen atom attracts another hydrogen atom. So everything attracts. So it has been there ever since the creation of the universe. Like ever since we know it, at least. Okay, so yeah, the pull of gravity is one of the fundamental forces of physics that just exists. Okay, Einstein tried to explain it with general relativity. Quantum gravity also tries to explain it, but there is no one unifying theory of gravity yet. We don't perfectly know for sure. Newton tried to explain it with Newton's law of gravity, and that's what we are studying now. Newton's law of gravity. It it works in most cases, but not in two large cases or not two small cases. Anyway, helium fuse করে কি form হবে? Guess what? What can form? A heavier nucleus than helium. Because hydrogen fuse করে কি form হয়েছে? A heavier nucleus than hydrogen, that is helium. So helium fuse করে কি form করবে? A heavier nucleus than helium. So the product of helium fusion reaction is gonna be either lithium or carbon, or basically তোমার হিলিয়ামের পরে যেগুলো পিরিয়ডিক টেবিল আছে, ঠিক আছে? So helium actually what it does is it helium nuclei fuse together to produce another isotope of helium first, helium 4, and then it they all again fuse into lithium, and then they fuse into carbon and so on. Okay, so just further elements of the periodic table. Neutron কই পাবে? Neutron কই পাবে? আচ্ছা হ্যাঁ, I haven't answered this question. এটা last বছর আসলে। So নিউট্রনটা কোথা থেকে আসে তাহলে? Well, hydrogen had a proton and an electron, and then hydrogen fusion led to the production of, well, helium. How did that happen? Well, there was not only hydrogen, and when I say hydrogen fusion, don't just think of the most available isotope of hydrogen, which is hydrogen 1 1. You also need to think about deuterium and tritium that you studied in chemistry. Deuterium and tritium, the other isotopes of hydrogen, those are also there, and they have neutrons. So yeah, there were neutrons. Okay, so neutrons are there from the beginning of the universe. Neutrons are there. By from the beginning, of course, I mean right after the expansion from where we are studying. Okay, so if it collapses, what will happen to the energy? It cannot be destroyed. Yes, of course, as you saw, the energy did not get destroyed, rather, the energy got accumulated in a small space, which triggered further helium nuclear fusion reactions and actually released more energy. Will sun expand and fall out? Well, you just saw that, yeah. Then আমরা কই যাব? Well, lucky for us, it's gonna happen 5 billion years later. So I don't think I need to worry about 5 billion years. I don't know about you. Okay. Um, I mean, Mars is always an option. Yeah, perfect. I like that. Yeah, Mars is always an option. It's gonna be a bad place to live in, but we can manage that. Can we stop that happening by providing it more hydrogen? No, no, no. Like the sun is a massive ball of hydrogen and helium. Like, where are you gonna get more hydrogen? You're gonna have to go to another star. And can you bring hydrogen from another star? No, that's not realistic. When it comes for temperature low হলে pressure কমে যাবে না and it will return to its original size. Temperature low হইলে আচ্ছা হ্যাঁ no even though the temperature is lower, understand that the temperature is lower at the surface. That is why the color is changing. But at the core, helium fusion reaction is still occurring. So once helium fusion reaction has started, at the core there is actually huge temperature. But since the star is now so big, not all of the energy from the core reach the surface, right? That is why the surface is cold. Okay, it's not that the entire star is cold. The surface is much cooler because of the large size of the star, because the energy is now distributed over such a large volume. That is why the temperature is lower, but the temperature at the core is still much higher. So nuclear fusion reaction will still continue, and at the core the pressure and temperature both are still more than sufficient to cause helium fusion reactions. What will happen if the sun expands after its stable? Yeah, that's what we just answered. After its stable period, the sun expands into a red giant. What is the core temperature of the sun? Well, you could just type that in Google. What is core temperature of sun? And Google will tell you 27 million degrees Fahrenheit, because Google is made by USA, who measure in the stupid unit of Fahrenheit. But in Kelvin, the temperature of the sun's core is about 15 billion, 15 million 700,000 Kelvin. So it's in degrees Celsius also about the same. So 15 million degrees Celsius or 15 million Kelvin. Is it possible that a star will expand as much to engulf about? Oh no, 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 hell no. Like, a star is large, it's huge, fine, but a star is much smaller compared to a galaxy. You need to remember the scale of the universe. There are billions of tiny stars. You remember that picture in which we showed the entire Milky Way, and each of those dots were stars? So stars are incredibly small. When I am talking about in terms of the galaxy, so black hole is at the center of the galaxy, and the galaxy is huge with billions of stars. So no, so we basically die by which does live. Yeah, you can say that. What is shockwave? Just a very large amount of energy released and huge amount of radiation pressure force in a very short time. Like, the when the main sequence star, the stable star, is turning into a red giant, there's a huge expansion, sudden expansion. That's a shock wave. Can helium turn to hydrogen again? No. I mean, not by nuclear fusion reaction, definitely. Nuclear fusion, remember this, nuclear fusion is the joining together of smaller nuclei to form a larger nucleus. Is helium larger or smaller than hydrogen? Helium is larger than hydrogen. So helium fusion cannot form hydrogen. Hydrogen fusion can form helium. Helium fusion can form lithium. Lithium fusion can form carbon. Carbon fusion can form oxygen, and so on. So heavier nucleus will only heavier nucleus will be produced by nuclear fusion, not smaller nucleus. Five calculation data, like again 5 বিলিয়নের ক্যালকুলেশনে তোমার এরর হইতে পারে 5-6 বছর, অথবা 5 বিলিয়ন ইয়ার্স এর মধ্যে যদি 100,000 ইয়ার্স এর ক্যালকুলেশনের এরর হয়, even that's not a problem, because 5 billion minus 100,000, if you do it in your calculator, 5 billion, that is 10 to the power 9. 5 in 10 to the power 9 minus 100,000, it will still be 5 billion. So the calculation error is insignificant here. Answer my question, go up. What was your question, lemon juice? Temperature low হইলে, I already answered that question. Temperature low হইলে কি হবে? I think you made this comment earlier. Okay. Point of singularity এর আগে কি ছিল? I love this question. I love this question. Point of singularity এর আগে কি ছিল? To the best of our knowledge, or rather to the best of the knowledge of the scientific community, if we read, okay, so time and space both started, both time and space began at the point of singularity. So let's say you ask, when will be next class? I can tell you a time. When you ask, if you ask, when was the last class? I can answer that in terms of time again. But the point of singularity is the beginning of time. So if you ask, what happened before the beginning of time, there is a fundamental problem with that question, because before time began, there is no before. Get it? Because before means past in time, but there is no before time began. So that's when time began. There is no before the point of singularity, there is only after the point of singularity. It's an amazing, it's a very, Stephen Hawking gave a very excellent description, like excellent interview on this question, and what I just told you is the conclusion from that interview. Okay, you can read that interview online, it's available. You can just Google Stephen Hawking interview about beginning of time. So yeah, that will give you that. Okay, what else do we have? 5 billion. Okay. Artistic Arthropod K, by the way. Who are you, by the way? That was a very good question. Thank you. What will happen if two black holes collide? We haven't even studied black hole. Be patient. We will study black holes and then we can talk about it. Can two stars engulf each other? Two stars can engulf each other, yes. There are some things, some stars in the universe called the twin stars. They're called twin stars. They orbit one another. Basically, they're like, how can I tell you this? Have you been on those um, kind of uh, Shishu Park rides where, like, you and your friend sit on two opposite sides and then it just rotates you, both of you? So imagine like both of you are two stars that are revolving each other, like that. So two stars spinning and revolving each other. So those stars, after a lot of spinning, sometimes do engulf each other and basically join together to form a bigger star. So black hole is the. I'll get to black hole at the end. That's messed up. Oh, artistic arthropod. That's messed up. Yeah, the beginning of time. Yeah, it is. Mofizuddin, answer my question. Mofizuddin, answer my question. Mofizuddin question ki chilo? What was your question? Instead of writing answer my question, you could just repeat your question. I cannot find your question among all the comments. Where is your question, Mofizuddin? There should be a search in the live chat. There's no search. That's sad. What are you doing, YouTube? Mofizuddin, you had one question. Are you kidding? I guess no, I wasn't. I couldn't find your question. Sorry about that. Okay. God was thinking, God was planning. Well, only God knows. Lithium fusion or carbon fusion possible? Yes, very much possible, and they do occur. We will see it in the next class. What is Omega Sanctuary? It's just the name of a star, I think. I'm not sure. I'll literally Google it. Yeah, I'll literally Google this. Omega Sanctuary is a global cluster in the constellation of Centaurus that was first identified as a non-stellar object. It is the largest globular cluster in the Milky Way at a diameter. It's a globular cluster. What the hell is a globular cluster? Um, it's a cluster of stars. Yeah, it's a cluster of stars. Yeah, it's basically a cluster of stars. It has approximately about 10 million stars. You can read the Wikipedia page for it. It's pretty detailed. It's nice. Yeah, you can read about it there. Sir, how the energy was created to start everything? Only God knows. We don't know. And I believe we will not know. Okay? Like, I strongly believe in the laws of physics, but if I tell you this, I'm gonna switch over to the PowerPoint just for a second. This is a rather philosophical discussion than a, but philosophy is just as important. So I'm gonna draw a timeline here, okay? If this is a timeline, right? And I mark a point here, okay? Now this line is in reality huge, like very huge, because this line represents the entire existing time of the universe from the beginning of time. This left end is the beginning of time, okay? So time began here and then we are at the end of this line. Now this point, we only know everything after this point. This time is about I think it was, last time I checked, was time when, you can Google this. I'm Googling. I'm actually searching this on Google. I think it was time when the fundamental forces were formed. Okay, so I can't find the exact value. Anyway, so the value is about, as far as I can remember, the value is about, I'll let you know the exact value later in your group chat, but the value is about 2 into 10 to the power, I think, minus 14 or something like that. Okay, this many seconds. Is that a very large time or a very, very, very short time? It is a very, very insanely short amount of time. Okay, and then after that time, the laws of physics, or rather the laws of universe are defined after this point, right after this point. So we can predict everything, like if two masses are left together, they will attract each other because gravitational force. If there are two types of charge, if they are like charges, they will repel. If they are unlike charges, they will attract. If there are two nuclei, if they join together, there will be nuclear fusion reaction, and the protons and neutrons are held together by strong nuclear forces, and then there one nucleus interacts with another nucleus with weak nuclear forces. All of those things, all the laws of physics, everything in the laws of the universe are defined. But at this point, these laws, all of those laws were unified. These laws were made like this small amount of time we know nothing about. We know absolutely nothing about this time. All we know is after this time, after the creation of the, after the big, after the starting of the point, this point is the point of singularity. So like just this small amount of time after the point of singularity, we know that the laws of physics are defined and we can explain everything. But what happened before then, why the laws of physics are the laws of physics, why this is there, that, why are we here, what's our purpose, these are philosophical questions that science has not been able to answer. And this is the point where I strongly believe in my religion that my purpose in life is to serve Allah. And that's where I will end today's class. Thank you. Allah Hafiz. Okay, I'll just answer your last few questions. Sir, how the energy was created? How we know that this is the time we missed? What's the age of the universe? We don't even know before. We know the age of the universe. We don't know before it, yes, but how do we know this is the time we missed? Like we can, like it's our prediction. Okay, it's a calculated prediction. It's a calculated guess. What's the age of the universe? 13.8 billion years. We will learn that calculation eventually. Not in this class, but in other levels. But we will learn it eventually. আর বুঝতেছি না এখন কিছু হ্যাঁ yeah, we're done, so don't worry about it. Welcome, how do you know? Assalamu alaikum everyone. About the small amount of time, but main kotha okay, Allah Hafiz. I'll end it here. Bye bye. See you in the next class.